In today's digital age, crimes often leave behind a trail of digital breadcrumbs. These traces exist on computers, servers, and even embedded devices. Linux, a powerful and versatile operating system, is no exception. Uncovering these digital secrets is the realm of Linux OS forensics, a specialized field that plays a crucial role in investigations. Imagine a scenario where a company suspects an employee of data theft. The employee primarily used a Linux workstation. Linux forensics experts can step in to investigate. They can analyze the employee's computer, piecing together their activities. By examining deleted files, internet history, and system logs, investigators can build a case. Linux forensics is not just about catching criminals, it can also help in incident response. For example, if a company's server is hacked, forensic investigators can determine the extent of the breach. They can identify the vulnerabilities exploited and recommend security improvements. The world of Linux forensics is vast and complex. This essay explores the key concepts and techniques used to uncover hidden evidence within Linux systems. Let's delve into the intricacies of this fascinating field. Before diving into the depths of Linux forensics, it's crucial to understand the underlying architecture of the Linux operating system. This foundational knowledge is essential for anyone looking to navigate the complexities of digital investigations within a Linux environment. This knowledge forms the foundation for comprehending how digital evidence is stored and how it can be extracted. Without a solid grasp of the Linux architecture, one might miss critical pieces of evidence or misinterpret the data. At the heart of the Linux OS lies the kernel. The kernel is the core component that serves as the brain of the operating system, orchestrating all its functions. This core component manages the system's resources. It handles everything from CPU scheduling to memory management, ensuring that each process gets the resources it needs to function efficiently. It acts as a bridge between the hardware and software, controlling everything from memory allocation to process execution. The kernel ensures that software applications can communicate effectively with the hardware, making it a critical component for system stability and performance. For forensic investigators, the kernel is a treasure trove of information. It maintains detailed logs of system activities which can be invaluable when trying to piece together the sequence of events leading up to a security incident. It logs system events, providing timestamps and details that can be vital for reconstructing events. These logs can reveal everything from login attempts to system crashes, offering a comprehensive view of what transpired on the system. Surrounding the kernel is the shell. The shell acts as an intermediary between the user and the kernel, translating user commands into actions that the kernel can execute. This user interface allows users to interact with the operating system through commands. Whether it's navigating the file system, managing processes, or configuring system settings, the shell provides a powerful interface for users to control the system. Forensic analysts can examine the shell's history to understand what commands a user executed, providing insights into their activities. By analyzing the command history, investigators can uncover evidence of malicious activities, such as unauthorized access or data exfiltration. Finally, we have the file system, the structure that organizes and stores data on a Linux system. The file system is where all the data resides, from system files to user documents, making it a critical area of focus in forensic investigations. Understanding the file system is paramount in Linux forensics. It provides the roadmap for locating and recovering digital evidence, whether it's active files, deleted files, or hidden data. It's here that we find remnants of deleted files, hidden directories, and other crucial artifacts. These remnants can offer clues about user activities and can be pivotal in building a timeline of events. In the next section, we'll delve deeper into the XT file system, a commonly used file system in Linux distributions, and explore its significance in digital investigations. The XT file system has unique characteristics that can aid forensic analysts in uncovering hidden or deleted data, making it an essential topic for anyone involved in Linux forensics. Among the various file systems employed by Linux distributions, the ext family, including ext2, ext3, and ext4, holds a prominent place. These file systems have evolved over time, each iteration bringing improvements in performance, reliability, and features. Understanding their evolution is key to grasping their forensic significance. Understanding the intricacies of these file systems is fundamental for any aspiring Linux forensics expert. Each version of the XT file system has its own unique characteristics and nuances that can impact forensic analysis. For instance, XT3 introduced journaling, which helps in faster recovery after a crash, while XT4 brought in features like extents and delayed allocation, enhancing performance and reducing fragmentation. Picture the XE file system as a well-organized library. Just as a library has a catalog system to keep track of books, the XT file system has structures to manage files and directories efficiently. At the top level, we have the superblock. This is akin to the library's main catalog, containing essential information about the entire collection. This master record contains crucial information about the file system. It holds details like the total number of blocks, the size of each block, and the location of other critical data structures. Without the superblock, the file system would be like a library without a catalog, making it nearly impossible to locate any book or file. It holds details like the total number of blocks, the size of each block, and the location of other critical data structures. Next, we have inodes. These are like the individual entries in the library catalog, each representing a specific book or file. Each file and directory within the XT file system has a corresponding inode. This inode contains all the metadata about the file, much like a catalog entry contains information about a book. These inodes act as pointers. They not only store metadata but also point to the actual location of the file's data on the storage medium. They store metadata about the file, such as its size, timestamps, and most importantly, pointers to the data blocks where the actual file content resides. This metadata is crucial for forensic investigators as it provides a timeline of file access and modifications. Finally, we have the data blocks themselves. These are the actual storage locations where the content of files and directories is kept. These blocks store the actual content of files and directories. When a file is accessed, the system follows the pointers in the inode to retrieve the data from these blocks. By following the pointers stored in the inodes, forensic investigators can reconstruct files, even if they've been deleted. This process involves piecing together the data blocks based on the information stored in the inodes. The structure of ext file systems presents both challenges and opportunities for forensic analysis. The complexity of these systems means that a deep understanding is required to effectively analyze and recover data. Deleted files, for instance, are not immediately erased from the storage media. Instead, their corresponding inodes are marked as available, and the data blocks are eventually overwritten. This delayed deletion process can be a goldmine for forensic investigators. Instead, their corresponding inodes are marked as available, and the data blocks are eventually overwritten. However, until that overwriting occurs, the data remains on the disk, accessible to those who know where to look. This means that remnants of deleted files can often be recovered, providing valuable evidence. Forensic experts use specialized tools and techniques to locate and reconstruct these remnants, turning what might seem like lost data into critical pieces of evidence. Section 4. Tools of the trade sleuthing through data. Forensic investigations would be a daunting task without specialized tools to navigate the complexities of digital evidence. The digital landscape is vast and intricate, filled with countless data points that can either reveal the truth or obscure it further. Investigators rely on these tools to sift through mountains of data, identify relevant information, and piece together the puzzle of what transpired. Fortunately, a range of powerful tools exist to aid investigators in their pursuit of the truth. These tools are designed to handle the unique challenges posed by digital evidence, from recovering deleted files to analyzing complex data structures. They provide the capabilities needed to uncover hidden information and ensure that no stone is left unturned. One such tool is the Sleuth Kit, or TSK, a command-line suite of utilities designed for forensic analysis. TSK is a robust and versatile tool that allows investigators to perform in-depth examinations of file systems. Its command-line interface may seem daunting at first, but it offers unparalleled control and precision for those who master it. TSK allows investigators to delve into the depths of file systems. They can explore the intricate details of how data is stored, accessed, and modified. This level of analysis is crucial for understanding the full context of digital evidence and uncovering hidden traces that might otherwise go unnoticed. They can examine deleted files, recover lost data, and analyze file system metadata with precision. This capability is essential for reconstructing events and understanding the actions taken on a digital device. By examining metadata, investigators can gain insights into the timeline of events, user activities, and potential tampering. For those who prefer a more user-friendly interface, Autopsy provides a graphical front end to TSK. Autopsy simplifies the process of forensic analysis, making it accessible to a wider range of users. Its intuitive interface allows investigators to perform complex tasks without needing to master command line operations. Autopsy simplifies complex forensic tasks, allowing investigators to visualize timelines, analyze file system activity, and generate comprehensive reports. These features are invaluable for presenting findings in a clear and understandable manner, both for internal use and in legal proceedings. These tools empower investigators to create forensic images of storage media, ensuring that the original evidence remains untouched. Forensic imaging is a critical step in the investigative process, as it preserves the integrity of the evidence while allowing for thorough analysis. They can then analyze these images, searching for specific files, carving out data from unallocated space, and reconstructing deleted files. Data carving is a technique used to recover fragments of files that may not be fully intact, providing additional pieces of the puzzle. The ability to recover and analyze data from Linux systems is essential in a wide range of investigations. Linux systems are commonly used in various environments, and understanding their file systems and data structures is crucial for comprehensive forensic analysis. Whether it's tracing the source of a cyber attack or reconstructing the timeline of an insider threat, these tools play a crucial role in bringing digital crimes to light. They enable investigators to follow the digital footprints left behind by perpetrators, uncovering the methods used and identifying those responsible. The combination of powerful forensic tools and skilled investigators is essential for solving complex digital cases and ensuring justice is served. Section 5. Unallocated space, where ghosts of data reside. When a file is deleted in a Linux system, it's not immediately erased from the storage media. Instead, the space occupied by the file is marked as unallocated, meaning it's available for reuse. However, remnants of the deleted file can linger in this unallocated space until they are overwritten by new data. This unallocated space is a goldmine for forensic investigators. By carefully analyzing this seemingly empty space, investigators can uncover fragments of deleted files, internet history, and other valuable artifacts. Specialized tools can scan unallocated space, piecing together remnants of deleted files based on file signatures and other characteristics. This process, known as file carving, can be instrumental in reconstructing past activities and recovering crucial evidence. The ability to recover data from unallocated space highlights the importance of preserving digital evidence as soon as possible. The longer a system is used after a potential crime, the higher the likelihood that unallocated space will be overwritten, potentially erasing valuable evidence.